Mars looks like a dead, frozen desert. But almost everything we see on its surface suggests that it wasn't always like this. At some point in the past, Mars had rivers, lakes, and possibly even an ocean. And whatever happened to it happened slowly enough to leave traces everywhere. What makes Mars unsettling isn't that it's different from Earth. It's that it may be showing us one possible future of our own planet. Tonight, we're going to move slowly through Mars, from its ancient surface to its vanished atmosphere, and to the quiet clues it left behind about how planets live and die. To understand Mars, we have to begin with what it is now. Not the Mars of imagination, but the Mars that exists today, turning slowly beneath a sky that hasn't seen rain in billions of years. Mars is the fourth planet from the Sun. It orbits about 225 million kilometers from Earth. One full Martian year takes 687 Earth days. But if you stood on Mars and counted its own days, you would find something familiar. A Martian day lasts 24 hours and 37 minutes. Just 37 minutes longer than an Earth day. It's close enough that human circadian rhythms could, with some effort, adjust. Close enough that the sun would rise and set in a way that wouldn't feel entirely alien. And there are other similarities. Mars is tilted on its axis, much like Earth. 25 degrees compared to Earth's 23.5. That tilt is what gives Mars its seasons. Winter and summer, spring and fall, each passing in their turn as the planet leans toward and away from the distant sun. The seasons last longer, of course, because the year is longer. But they exist. From a distance, Mars glows with a color that has captivated humans for thousands of years. Red. Not the red of fire or blood, but something duller, older. The red of rust. The entire surface of Mars is covered in a fine layer of dust, and that dust is rich in iron oxide, the same compound that forms when iron meets water and oxygen and time. The planet is, in a literal sense, rusting. But Mars is smaller than Earth, much smaller. If you placed the two planets side by side, Mars would look almost fragile. Its diameter is just over half that of Earth's. Its mass is only about 1/10. If you stood on the surface of Mars, you would weigh roughly a third of what you weigh here. Gravity would pull at you, but more gently. The atmosphere of Mars is almost non-existent. Its pressure is less than 1% of Earth's. If you stepped outside without a suit, your blood would boil almost instantly, not from heat, but from the sudden absence of pressure. The air is 95% carbon dioxide. There is almost no oxygen, no nitrogen worth speaking of, nothing that could sustain a human life for more than a few seconds. The temperature on Mars swings violently. At the equator during summer, it might reach 20 degrees Celsius. But as the sun sets, the temperature plummets. By dawn, it could be 100 degrees colder. At the poles, in the depth of winter, temperatures drop to minus 140 degrees Celsius. Cold enough to freeze carbon dioxide out of the air. Cold enough that the polar caps grow visibly larger as the seasons turn. This is Mars as it exists now, a world of extremes. A world where a day feels almost like home, but where the air would kill you in moments. A world that is red because it has been rusting for billions of years. But the rust itself is a clue. Iron oxide requires water, and water, once, was everywhere on Mars. The water left evidence everywhere, not just in dried riverbeds and ancient shorelines, but in something more fundamental, in the minerals themselves. Iron oxide, the rust that colors the entire planet red, only forms when iron meets water and oxygen. Every grain of Martian dust is a record of water's presence. But there is another kind of evidence written into the surface of Mars. Evidence of forces that shaped the planet long before the water disappeared. Forces that built mountains so vast they dwarf anything on Earth. On the western edge of Mars, in a region called Tharsis, there is a mountain so large that it challenges the very idea of what a mountain can be. Its name is Olympus Mons. Mount Olympus, in the language that once named the home of gods. Olympus Mons rises 22 kilometers above the surrounding plain. Mount Everest, the tallest mountain on Earth, stands less than 9 kilometers high. Olympus Mons is 2.5 times taller. But height alone doesn't capture what Olympus Mons truly is. If you could stand at its base and look toward the summit, you wouldn't see a towering peak. You would see a slope. A gentle, almost imperceptible rise that stretches toward the horizon and beyond. Because Olympus Mons is not just tall, it is enormous in every dimension. The volcano is 600 kilometers wide. From one edge to the other, it would cover the entire state of Arizona. If you placed it over France, it would blanket the country from border to border. The sheer scale is difficult to hold in your mind. A mountain the size of a nation. And yet, if you were standing on the slope of Olympus Mons, you might not realize you were on a mountain at all. The incline is so gradual, averaging only about 5 degrees, that it would feel more like walking across a vast, tilted plain. You could hike for days, climbing steadily upward, and never see a dramatic peak ahead of you. The summit would be beyond the horizon, hidden by the curvature of the slope itself. This is what defines a shield volcano. Not a steep, explosive cone, but a broad dome built slowly, layer by layer, from lava that flows rather than erupts. Olympus Mons grew this way over billions of years. On Earth, shield volcanoes like those in Hawaii are eventually carried away by the movement of tectonic plates. The Pacific Plate drifts over a stationary hotspot deep in the mantle, and each volcano is born, grows, and then is carried off, leaving the hotspot to build a new mountain in its place. This is why the Hawaiian Islands form a chain, each island representing a different stage in the life of the same volcanic source. But Mars has no tectonic plates. Its crust is frozen in place, locked and unmoving. When a hotspot formed beneath the surface of Mars, the volcano that rose above it stayed there. For hundreds of millions of years, lava poured from the same location, piling higher and higher, spreading wider and wider. There was no plate to carry it away, no limit to how large it could grow. The summit of Olympus Mons is marked by a caldera 85 kilometers across. Not one crater, but several, nested inside each other. Each formed when the magma chamber drained and the ground collapsed inward. The last major eruption from Olympus Mons happened 25 million years ago. That sounds ancient by human measures. 25 million years ago, Earth was in the Miocene epoch, and the ancestors of modern apes were just beginning to diverge. But in geological time, 25 million years is recent. Recent enough that some scientists believe Olympus Mons may not be truly extinct, only dormant, waiting. The peak of Olympus Mons rises so high that it reaches above much of Mars's already thin atmosphere. At the summit, the atmospheric pressure is only 12% of the average pressure at the Martian surface. 12% of almost nothing. If you stood there, you would be standing, in a sense, at the edge of space. There is something quietly unsettling about a volcano this size, a structure so massive that it bent the planet beneath it. A mountain built over billions of years by forces we can barely comprehend, and which may, even now, not be finished. Olympus Mons is not alone. It sits near 3 other enormous shield volcanoes, all part of the Tharsis region. Together, they form a volcanic province unlike anything on Earth. And their combined weight did something extraordinary to Mars, something that changed the planet's entire face. 3 billion years ago, the weight became too much. Olympus Mons was not the only giant rising in Tharsis. 3 other enormous shield volcanoes stood nearby, aligned in a rough diagonal across the landscape. Ascraeus Mons, Pavonus Mons, and Arsia Mons. Each one dwarfing any mountain on Earth. Each one pouring lava onto the Martian surface for hundreds of millions of years. Together, they built a dome. The Tharsis region is not just a collection of volcanoes. It is a plateau 5,000 kilometers wide and 7 kilometers high. The mass weighs roughly 1/70th the mass of Earth's moon. 1 billion tons. For a time, the crust held. But Mars is smaller than Earth, and its interior had already begun to cool. The tectonic forces that might have redistributed such weight on a larger, more active planet were absent. The load simply sat there, unmoving, growing heavier with each eruption. And then, slowly, the planet began to tip. Not a sudden catastrophe, but a gradual reorientation that took millions of years. The outer layers of Mars, the crust and the mantle, shifted around the core. They rotated by 20 to 25 degrees, moving the Tharsis dome from its original position toward the equator. The dome itself stayed fixed relative to the interior of the planet, but everything on the surface moved. Rivers changed course. Polar ice migrated to new latitudes. The entire geography of Mars was rewritten. If you could have watched this happen, you would have seen the surface of Mars slowly twist. Ancient rivers would find themselves flowing in new directions. Features from frozen latitudes would drift toward temperate zones. The evidence for this tilt is written into the planet's surface in ways that scientists only recently learned to read. River valleys, mapped from orbit, cluster in a band across what was once a tropical region. But that band doesn't align with Mars's current equator. It's offset, rotated by about 20 degrees. When researchers removed the Tharsis bulge mathematically, simulating what Mars might have looked like before the volcanoes formed, the river valleys snapped into alignment. They followed the climate patterns you would expect on a planet with an axial tilt. Precipitation falling in a belt near the ancient equator, carving channels as it ran downhill toward the lowlands. The tilt also explains ancient glaciers found far from the current poles. Ice-transported debris and erosion patterns that only make sense if the poles were once somewhere else. The shift happened after most of the river valleys had already been carved, after the era of flowing water had largely ended. The best estimates place the tilt at around 3 to 3.5 billion years ago, a time when Mars was transitioning from a wetter, more active world to the cold desert it is today. The tilt didn't cause the water to disappear, but it may have accelerated the process. When the surface rotated, climates shifted. Regions that had been warm enough to sustain liquid water found themselves in colder latitudes. Ice that had been locked at the poles migrated to new locations. The redistribution of mass, of ice and rock and atmosphere would have changed wind patterns, temperature gradients, the very circulation of what little air remained. It's difficult to imagine a planet-scale event like this. We think of planets as stable, unchanging on human timescales. But Mars was not stable. Its crust floated, in a sense, on a partially molten interior, and when the weight on one side became too great, the whole outer shell of the planet slipped. Not by inches, but by thousands of kilometers. The Tharsis volcanoes sit near the equator now, where they have been for billions of years. But they were born elsewhere. They grew so massive that they dragged the surface of Mars into a new configuration, one that placed them where the planet's spin could better balance their weight. And in doing so, they erased the old Mars. The planet that existed before the tilt is gone, buried under new geography, its rivers flowing in directions that no longer make sense, its ice resting in places it can no longer reach.
The reshaping of Mars left scars. Some are subtle, visible only in the patterns of ancient riverbeds or the placement of ice deposits. But one scar is impossible to miss. Stretching across the face of Mars, just south of the equator, there is a canyon system so vast that it defies easy comprehension. Valles Marineris, the Valleys of Mariner, named after the spacecraft that first photographed it in detail. Valles Marineris is 4,000 kilometers long. To understand that distance, imagine a crack in the ground that begins at the northern tip of Norway and extends all the way to the southern coast of Sicily, or a canyon that stretches across the entire United States, from the Pacific coast to the Atlantic. That is the scale of Valles Marineris. At its widest, the canyon spans 200 kilometers. At its deepest, it plunges 7 kilometers below the surrounding plateau. 7 kilometers straight down into the Martian crust. For comparison, Earth's Grand Canyon is about 800 kilometers long, 30 kilometers wide at its broadest, less than 2 kilometers deep. Valles Marineris is 10 times longer, 20 times wider, and 5 times deeper. If you placed the Grand Canyon inside Valles Marineris, it would fit comfortably into one of the side canyons. But size alone doesn't explain what Valles Marineris truly is. The Grand Canyon was carved by water, by the patient work of the Colorado River, cutting through layers of sedimentary rock over millions of years. Valles Marineris was not carved by water. It is a tectonic feature, a crack. Billions of years ago, as the Tharsis bulge grew under the weight of its volcanoes, the crust of Mars stretched. Imagine the surface of the planet as a thin shell, floating on a partially molten interior. As Tharsis rose, the crust around it had to accommodate the deformation. In some places, it buckled. In others, it pulled apart. The rock stretched like a sheet being pulled from opposite ends, thinning, weakening, until finally it fractured. Valles Marineris is the result of that fracturing, a rift zone that opened as the planet's surface adjusted to forces it could not fully withstand. The canyon begins in the west, at a region called Noctis Labyrinthus, the Labyrinth of Night, a maze of interconnected valleys and collapsed terrain, fractured into a chaotic jumble of blocks and depressions. From there, the canyon extends eastward, splitting into multiple parallel chasms, each one massive in its own right. Ias Chasma, Tithonium Chasma, Melas Chasma, Coprates Chasma, names that mark individual sections of a system too large to comprehend as a single feature.
Each chasma is itself larger than any canyon on Earth. Some sections of Valles Marineris show clear signs of tectonic activity. Long, straight walls, where the ground simply dropped away along fault lines. Others show evidence of later modification. Landslides that carried debris as far as 60 kilometers from the canyon walls. Layered deposits on the canyon floor that hint at sediments laid down in water, or perhaps by wind, long after the initial fracture formed. There are places in Valles Marineris where the depth is so extreme that if you stood at the rim and looked down, the bottom would be lost in shadow and haze. The deepest sections plunge 11 kilometers below the surrounding terrain. Mount Everest, placed at the bottom of the canyon, would not reach the rim. Even in the thin Martian atmosphere, the sheer vertical distance creates perspectives that feel impossible. The canyon runs for nearly a quarter of the planet's circumference. If you walked along its length at a steady pace, it would take months. If you tried to cross it at its widest point, you would need days just to reach the other side. And yet, from orbit, Valles Marineris looks almost delicate. A dark scar cutting across the rusty surface of Mars, narrow in comparison to the width of the planet, but unmistakable. A reminder that even a world as small and cold as Mars has been shaped by forces powerful enough to split continents. Valles Marineris is not the result of erosion wearing down the surface. It is the result of the surface pulling itself apart. A wound in the crust of Mars that has never healed, preserved in the thin, dry air for billions of years. The canyon is empty now. No rivers flow through it. No glaciers carve its walls. It simply exists, vast and silent, a monument to a time when Mars was still geologically active enough to tear itself open. For a long time, the idea of an ocean on Mars belonged more to imagination than to evidence. Rivers and lakes were one thing, but an ocean implied something larger, more stable, more Earth-like. And yet, over the past few decades, a quiet accumulation of data has begun to suggest that Mars may once have held exactly that: an ocean. Roughly 3.5 billion years ago, during Mars's early history, the planet was very different from what we see today. Its atmosphere was thicker, its surface warmer. Liquid water could exist for long periods without instantly freezing or evaporating. At that time, much of Mars's northern hemisphere sat lower than the southern highlands. A vast, gently sloping basin stretched across the planet's north. Today, it looks empty, but in the past, it may have been filled. Multiple lines of evidence point to the same conclusion: that water flowed downhill from the southern highlands, that it pooled in the north, and that, over time, it collected into something enormous. Scientists estimate that this ancient body of water may have covered roughly 1/3 of the planet's surface, an ocean spanning millions of square kilometers. Shallow in some places, deeper in others, but persistent enough to shape the land around it. The evidence is not a single feature. It is a pattern. Ancient shorelines trace long, curving paths across the northern plains. Not sharp cliffs, but subtle, eroded boundaries. They follow consistent elevations. They wrap around the basin as coastlines would. In several regions, river valleys terminate abruptly at the edge of the lowlands. They do not taper off. They end, as if they once emptied into something larger. Orbital images reveal fan-shaped deltas where sediment spread outward, layer by layer. Structures that form when rivers slow down and drop their load. On Earth, these are signatures of standing water. On Mars, they appear frozen in time. In recent years, some of the strongest evidence has come not from orbit, but from the surface itself. In the northern plains, China's Zhurong rover used ground-penetrating radar to peer beneath the dust. What it found was unexpected. Below the surface were gently sloping layers, not chaotic, not fractured, but arranged in orderly patterns, inclined at angles consistent with sediment deposited by waves, structures strikingly similar to ancient beach formations on Earth. These layers were buried, protected from erosion for billions of years. They were not carved by wind. They were not laid down by lava. Their geometry suggests repeated interaction with water, with motion, with time. Taken together, the shorelines, the deltas, the sedimentary layers, and the subsurface structures all tell the same story. Water did not merely pass through Mars. It stayed. For how long, scientists are still refining their estimates. Perhaps tens of millions of years, perhaps longer. Long enough to reshape the planet's surface. But if Mars once had an ocean, a larger question follows naturally. Where did it go? Some of the water escaped into space. Mars's gravity is weak, and its magnetic field faded early. Without protection, the atmosphere was slowly stripped away by the solar wind. As the air thinned, liquid water became unstable. It evaporated. And once in the upper atmosphere, it was lost. Some of the water froze. Today, large amounts of ice remain locked in the polar caps and buried beneath the surface. Radar surveys suggest frozen water still lies hidden just meters below the soil in many regions. And some of the water never left at all. Instead, it became part of the planet, bound into minerals through chemical reactions, trapped in clays formed when water altered the crust. Mars did not lose its water in a single catastrophe. It faded, slowly, as volcanic activity declined, as the interior cooled, as the atmosphere thinned and failed. What remains today are traces, subtle, fragmented, but consistent. Enough to say that Mars was once not just wet, but stable, for a time. The ancient ocean of Mars is not a certainty carved in stone. There are still debates, unanswered questions. But the evidence has grown too coherent to ignore. Mars was once a world where water gathered, rested, and reshaped the land. And in that fact, Mars becomes more than a dead planet. It becomes a record, a reminder that even slow changes, given enough time, can empty a world. When we talk about water on Mars, it's easy to think only in terms of the past. Ancient rivers, vanished lakes, a lost ocean. But Mars may not be entirely dry even now. The water may simply be hidden. Far beneath the cold, lifeless surface, scientists believe that liquid water may still exist. Not in rivers, not in lakes, but locked deep underground. The evidence comes from vibrations, from Mars quakes, from the way sound waves move through the planet's interior. In 2018, NASA's InSight lander touched down on the Martian surface. Unlike rovers designed to roam, InSight stayed in one place. Its purpose was not to explore the surface, but to listen. InSight carried a seismometer sensitive enough to detect tiny tremors passing through Mars. Each quake sent waves downward, through layers of rock, then back up again. By measuring how fast those waves traveled, scientists could infer what lay beneath. Over time, a pattern emerged. At depths between roughly 10 and 20 kilometers, seismic waves slowed down. Not enough to suggest molten rock, not enough to imply empty space, but consistent with something else. Liquid water. The water is not free-flowing. It is trapped within fractured rock, soaking into pores and cracks under immense pressure, kept liquid by the heat of the planet's interior, even as the surface above remains frozen. Based on the seismic data, researchers estimate that the total volume of this underground water is enormous. Enough, if brought to the surface, to cover the entire planet to a depth of 1 to 2 kilometers. More water than existed in many of Mars's ancient surface seas. This discovery changes the way scientists think about Mars. Because liquid water is not just a geological detail, it is a biological one. On Earth, life exists wherever liquid water persists. In deep rock, in underground aquifers, in environments completely cut off from sunlight. Some organisms survive on chemical energy alone, feeding on minerals and heat. If similar conditions exist beneath Mars, then the planet may still be habitable in a limited sense. Not on the surface, but below it. This does not mean that life exists there now. There is no direct evidence, no samples, no organisms detected. But the presence of long-lived liquid water dramatically extends the window of possibility. If life ever arose on Mars when surface water was abundant, it may not have vanished entirely. It may have retreated downward. The underground reservoirs could have acted as refuges, sheltered from radiation, protected from atmospheric loss, stable over billions of years. And even if Mars is sterile today, these reservoirs preserve a record. Water that has interacted with rock since the planet's early history. Water that may still carry chemical signatures of past environments. Reaching this water will not be easy. Drilling 10 or 20 kilometers into another planet is beyond current technology. For now, the evidence remains indirect, inferred, measured through vibrations and mathematics. But the implications are profound. Mars may not be a world where water simply vanished. It may be a world where water withdrew, hidden beneath the surface, waiting. The surface of Mars tells a story of loss, but the interior may be telling a different one, a quieter story, one that is still unfolding. High above the surface of Mars, a small moon is slowly falling. Not suddenly, not violently, but steadily, year by year. Its name is Phobos. Phobos is the larger of Mars's two moons, but it is small by planetary standards, irregular in shape, dark, only about 20 kilometers across. What makes Phobos remarkable is how close it orbits. At its lowest point, it passes only a few thousand kilometers above the Martian surface, closer to its planet than any other moon in the solar system. So close that its motion across the sky is rapid and strange. From the surface of Mars, Phobos does not behave like a normal moon. It rises in the west, it sets in the east. Because Phobos orbits Mars faster than Mars rotates, it appears to move backward across the sky. In a single Martian day, it can rise, cross overhead, set, and then repeat the cycle again. 2 brief appearances, each lasting only a few hours. This unusual orbit comes at a cost. Phobos is not stable. It is slowly losing altitude. Measurements show that Phobos is spiraling inward at a rate of about 1.8 centimeters per year. A distance too small to notice in a human lifetime, but over millions of years, it becomes decisive. The cause is gravity. Tidal forces between Mars and Phobos are draining energy from the Moon's orbit. As that energy is lost, Phobos moves closer and closer. Phobos already orbits within a region where tidal forces are strong, a zone where a moon can no longer remain intact indefinitely. As it descends, those forces increase. Stress builds within its interior. Long grooves and fractures etched across Phobos' surface may already be signs of this strain, evidence that the moon is being slowly pulled apart. Its fate is not in doubt, only the timing and the exact form it will take. Current models suggest that in roughly 30 to 50 million years, Phobos will reach a critical point. At that time, it will either break apart or fall. One possibility is that Phobos will be torn into fragments before it ever reaches the surface. Those fragments would spread along its orbit, forming a temporary ring around Mars. Thin, faint, short-lived on cosmic timescales. The other possibility is a gradual collapse followed by impact. Pieces of Phobos could strike Mars over time, leaving scars on the surface. Not a single event, but a drawn-out ending. In either case, the process is slow. There is no explosion, no sudden catastrophe, just the steady pull of gravity, working over immense spans of time. Phobos offers something rare, a planetary process we can observe while it is happening. Orbital decay, tidal stress, a moon in the final chapter of its existence. While Earth's moon slowly drifts away from us, Phobos moves inward. A reminder that celestial systems do not all evolve in the same direction. Mars will not keep this moon forever. Phobos is already on its last path, moving inward, year by year, centimeter by centimeter. On the scale of the universe, 30 million years is soon. And when Phobos is gone, Mars will once again orbit the Sun alone. A planet shaped by loss, still changing. On Mars, weather does not always arrive gently. Sometimes it grows until it consumes the entire planet. Dust storms on Mars can begin small, a local disturbance, winds lifting fine particles from the surface, a haze spreading across a single region. But Mars is uniquely vulnerable to dust. Its soil is dry, its gravity is weak, and its atmosphere, though thin, can carry dust high and far. As a storm grows, it feeds on sunlight. Dust in the air absorbs solar energy, warming the atmosphere. That warmth strengthens winds. Stronger winds lift more dust. A feedback loop begins. Local storms merge into regional ones. Regional storms expand, and sometimes the process does not stop. Roughly every 3 Martian years, Mars experiences a global dust storm. an event so large that it can wrap around the entire planet, from pole to pole. When this happens, Mars changes. The sky darkens. Sunlight struggles to reach the surface. From orbit, the planet's familiar markings fade beneath a thick, reddish veil. These storms do not last days. They last weeks, sometimes months. During a global storm, sunlight reaching the surface can drop to a fraction of normal levels. Solar-powered spacecraft depend on that light. Without it, they cannot survive. In 2018, one such storm enveloped Mars. At the time, the Opportunity rover had been exploring the surface for nearly 15 years. Designed for a mission lasting 90 days, it had already far exceeded expectations. As the storm intensified, Opportunity's solar panels were starved of light. Power levels fell. Communications ceased. Engineers listened. They called, but the rover never answered. The storm had taken it. Dust storms also change Mars' temperatures. Near the surface, days grow colder as sunlight is blocked. Higher in the atmosphere, temperatures rise as dust absorbs heat. The entire climate system shifts. Winds accelerate, pressure patterns change, and the storm sustains itself until the dust finally settles. Nothing like this happens on Earth. Our planet's storms are limited by oceans, vegetation, and a dense atmosphere. Mars has none of these stabilizing forces. A regional dust storm on Mars can be comparable in size to a continent on Earth. A global storm has no earthly equivalent. It is not a hurricane, not a monsoon, but something entirely planetary. Eventually, the dust falls back to the ground. The sky clears. Sunlight returns. Mars emerges once again. But each storm leaves its mark. Dust redistributed across the surface. Spacecraft lost. Energy budgets altered. These storms are not just dramatic. They are part of how Mars works, how it breathes, how it changes. On Mars, even the weather reminds us that this is a world still in motion. Thin, fragile, and capable, at times, of swallowing itself.
On Mars, there is a gas that should not behave the way it does. Methane. Methane is a simple molecule. 1 carbon atom, 4 hydrogen atoms. On Earth, it is common and well understood. Produced by living organisms, geological reactions, and human activity. But on Mars, methane has become one of the planet's most persistent and unsettling mysteries. For years, instruments have detected faint traces of methane in the Martian atmosphere. The background level is extremely low, only a few tenths of a part per billion, barely enough to measure. And then, without warning, it changes. NASA's Curiosity rover has recorded sudden spikes in methane concentration, brief surges that rise as much as 40 times above the background level. They appear rapidly. They disappear just as quickly. Sometimes the increase lasts a few days. In some cases, methane rises overnight and vanishes again by the next morning. This behavior is deeply unexpected. Under known Martian conditions, methane should persist in the atmosphere for hundreds of years. Sunlight alone cannot destroy it fast enough. Known chemical reactions are far too slow. Yet the methane detected by Curiosity does not linger. Something is adding it, and something is removing it. The pattern is not random. Long-term measurements show clear seasonal variations. Methane levels tend to rise during certain parts of the Martian year and fall during others.
There are also indications of differences between day and night. These patterns suggest that the source lies close to the surface, and that its release responds to temperature, pressure, or sunlight. What could be producing it? There are two broad possibilities: biology or geology. On Earth, a significant fraction of methane is produced by microscopic life. Certain microbes generate methane as a metabolic byproduct, often in dark, oxygen-poor environments. If similar organisms exist beneath the Martian surface, protected from radiation and extreme cold, they could release methane intermittently. But there is no direct evidence for life on Mars today. No organisms have been observed. No biological material has been confirmed. Methane alone is not proof. The geological explanation does not require life. Certain chemical reactions between water and iron-rich rocks can generate methane naturally. One such process, known as serpentinization, occurs when water interacts with specific minerals deep underground. These reactions can operate slowly and silently for millions of years. Another possibility focuses not on production, but on storage. Methane may already exist beneath the surface, trapped, waiting. Mars's soil contains abundant salts. Under the right conditions, these salts can form crusts and mineral layers. Laboratory experiments and physical models suggest that such salt deposits can trap gases, including methane, within microscopic spaces. When temperatures shift, when pressure changes slightly, or when sunlight alters surface chemistry, the trapped methane may be released suddenly. A brief plume, a sharp spike, then silence again. This mechanism could explain both the intensity of the spikes and their rapid disappearance. Methane released near the surface could be quickly broken down by chemical reactions or absorbed back into the soil before it spreads. Adding to the mystery is a disagreement between instruments. Surface measurements detect methane spikes, but orbiting spacecraft sometimes detect almost nothing at all. This suggests that methane releases may be highly localized and short-lived, confined close to the ground, gone before they can mix into the wider atmosphere. At present, there is no single explanation that accounts for every observation. Not biology alone, not geology alone, not chemistry alone. The methane mystery remains unresolved, but it is not stagnant. Each new measurement adds a constraint. Each detection narrows the range of possibilities. Mars may be telling us that its interior is still active, that its surface chemistry responds to subtle environmental changes, or that processes beneath the ground continue to interact with the thin air above. For now, methane on Mars is not an answer. It is a question. A recurring signal from a planet that still refuses to be fully understood. Brief, elusive, and impossible to ignore. For a long time, Mars was protected. Not by distance, not by luck, but by an invisible shield generated deep inside the planet itself. Early in its history, Mars possessed a global magnetic field, a true planetary shield, similar in purpose to Earth's magnetic field today. It surrounded the planet and extended far into space, deflecting charged particles streaming outward from the sun. This magnetic field was not a surface feature. It was born in the depths of the planet. Deep beneath the crust, Mars once had a hot, molten, metallic core. Liquid iron flowed and circulated, driven by internal heat left over from the planet's formation. That motion created a planetary dynamo. As long as the core remained hot and active, Mars remained shielded. During this early era, Mars was not the barren world we see today. Its atmosphere was thicker, surface pressure was higher, temperatures were more moderate. Liquid water could exist without instantly freezing or boiling away. Rivers carved valleys, lakes filled basins, Possibly even oceans covered parts of the surface. But Mars is a small planet, only about half the diameter of Earth, and when it comes to planetary survival, size matters. Smaller planets lose heat faster than larger ones. They have less internal energy to sustain long-term activity. Over time, Mars began to cool from the inside out. The heat driving motion within its core slowly diminished. As the planet cooled, the molten iron within the core became less mobile. Convection slowed. The organized flow required to sustain the dynamo weakened, and eventually, it failed. When that happened, Mars lost its global magnetic field. The shield collapsed. The timing of this loss was early in the planet's history, likely within the first few 100 million years after Mars formed, long before the planet became the frozen desert we see today. Once the magnetic field disappeared, Mars was exposed, directly, completely. The Sun emits a constant stream of charged particles known as the solar wind. On Earth, this flow is largely deflected by our magnetic field. Mars no longer had that protection. Without a magnetic field, the solar wind interacted directly with Mars' upper atmosphere. High-energy particles struck atmospheric atoms and molecules. Some particles were heated enough to escape Mars' gravity. Others were knocked free by direct collisions. Bit by bit, the atmosphere was eroded. Not all at once, not violently, but relentlessly. This was not a single catastrophic event. Mars did not lose its air overnight. The process unfolded slowly, over hundreds of millions of years. NASA's MAVEN spacecraft has observed this process directly. It has measured atmospheric particles escaping into space, confirmed that atmospheric erosion continues even today. As the atmosphere thinned, surface conditions began to change. Air pressure dropped, temperatures declined, liquid water became increasingly unstable. Water that once flowed freely across the surface evaporated more easily. Once water vapor reached the upper atmosphere, sunlight broke the molecules apart. Hydrogen escaped readily into space. Oxygen either followed or reacted with surface rocks. Some water froze beneath the surface. Some became locked in polar ice. Some was chemically bound into minerals. But a large fraction was lost forever. The loss of the magnetic field set this entire chain in motion. Core cooling, shield collapse, atmospheric erosion, water loss, climate decline. Mars did not lose its habitability in a single moment. It faded, slowly, as each protective layer failed in turn. By the time rivers dried up and lakes disappeared, the outcome was sealed. The atmosphere was too thin, the surface too cold, the shield long gone. Earth followed a different path. Our planet is larger. Its core remains hot and dynamic. Its magnetic field still stands, preserving the atmosphere, protecting surface water. Mars shows us the alternative. What happens when a planet loses its internal heat, when its shield collapses? The planet did not die in a dramatic instant. It unraveled, layer by layer, over immense spans of time. Mars lost its shield, and once it did, the rest followed.
Mars is known as the Red Planet. Its surface is coated in iron-rich dust. That dust colors the rocks, the ground, and even the sky itself. For most of the Martian day, The sky appears hazy and reddish, tinted by countless fine particles suspended in the thin air. But when the sun sets on Mars, the colors behave in a way that feels almost backwards. Instead of turning red, the sky around the sun turns blue. This is not an illusion. It is not an artistic enhancement. It is a real phenomenon that has been observed directly from the surface of Mars. NASA's rovers have photographed it multiple times. Curiosity first captured blue-tinged sunsets from Jezero Crater. Years later, Perseverance confirmed the same effect using its Mastcam Z cameras. These images were carefully calibrated. Scientists corrected them to match how human vision would perceive the scene. The blue color is not exaggerated. It is physical. To understand why this happens, it helps to compare Mars with Earth. On Earth, the daytime sky is blue because air molecules scatter short wavelengths of light more efficiently than long ones. This process is known as Rayleigh scattering. Blue light is scattered in all directions, filling the sky overhead. At sunset on Earth, sunlight travels through a much longer path in the atmosphere. Most of the blue light is scattered away before it reaches your eyes. The remaining light is dominated by longer wavelengths. Reds and oranges take over. Earth's sunsets are red. Mars is different. Its atmosphere is extremely thin, with less than 1% of Earth's surface pressure. And instead of being dominated by gas molecules, the Martian atmosphere is dominated by dust, fine particles suspended throughout the air. These dust particles are very small, roughly the same size as the wavelengths of visible light. That places them in a different scattering regime. Not Rayleigh scattering, but Mie scattering. Mie scattering behaves differently. Rather than scattering light evenly in all directions, it tends to scatter light forward, in the direction the light is already traveling. And under Martian conditions, this forward scattering favors shorter wavelengths near the sun. As the sun approaches the horizon, its light passes through more dust. Red light is scattered broadly across the sky, tinting the landscape and the air. Blue light, however, is scattered forward and remains concentrated close to the sun's position. The result is a striking reversal of Earth's familiar pattern. Away from the sun, the sky looks reddish, but near the sun, a cool blue halo appears. Subtle, muted, distinct. This blue coloration is narrow and localized. It does not fill the entire sky. It forms only around the sun during sunrise and sunset, and it lasts only a short time. The effect depends on the amount of dust in the atmosphere. If the air is too clear, the blue halo is weak. If the air is thick with dust, the sun dims and the colors soften. The most vivid blue sunsets occur when dust levels are moderate. Scientists study these sunsets carefully. The exact shade of blue provides information about the size of dust particles. The brightness reveals how dust is distributed vertically in the atmosphere. Changes in color over time can indicate shifts in weather patterns or seasonal circulation. In this way, Martian sunsets are not just visually striking, they are scientific tools. Natural experiments repeated every Martian day. Rover observations have confirmed that this effect is consistent across locations and missions. Pathfinder hinted at it decades ago. Curiosity documented it clearly. Perseverance refined the measurements with modern instruments. The physics holds. There is also a quiet contrast in these scenes. Mars is a world shaped by harsh conditions: thin air, cold temperatures, constant dust. And yet, at sunset, it offers something unexpectedly gentle. If you were standing on the surface of Mars,
You would watch the sun sink toward the horizon. The reddish sky would darken. The landscape would fade into shadow. And then, just before the sun disappeared, blue would emerge around it. Cool, brief, precise. It is one of the few times Mars displays a color Earth does not. A reminder that the same physical laws operate everywhere, but produce different outcomes under different conditions. Blue sunsets on Mars are no longer a mystery. They are explained by physics, confirmed by observation, repeated by multiple missions. Yet they remain something rare. A moment of calm on a planet defined by extremes. A blue farewell on the red planet. Mars has been searched for many things. Water, atmosphere, geological history. But more than anything else, it has been searched for life. Not complex life, not animals or plants, but something far smaller, something simpler, something that could have existed billions of years ago when Mars was a very different world. One of the most important discoveries made on Mars is the detection of organic molecules, carbon-based compounds that form the chemical backbone of life on Earth. NASA's Curiosity rover found these molecules preserved in ancient sedimentary rocks inside Jezero Crater. These rocks are more than 3 billion years old. They were once part of lake beds and muddy sediments. Over time, minerals encased the organic material, shielding it from radiation and chemical destruction. Against long odds, the molecules survived. Organic molecules do not prove life. They can be created by non-biological processes, but their presence matters, because they show that the basic ingredients for life were available, and that they can persist on Mars for immense spans of time. Mars also preserves evidence of environments that could have supported life. Ancient river channels cut into the surface, deltas formed where water slowed and deposited sediment, minerals called clays, which only form in liquid water with relatively mild chemistry. These are not signs of brief flooding. They point to stable, long-lasting environments. Lakes that existed for thousands, possibly millions of years. On Earth, such environments are ideal habitats for microbial life. Chemical energy sources were also present. Differences in mineral composition created gradients that microbes on Earth readily exploit. Energy does not require sunlight, only imbalance. Mars had plenty of that. Today, the search for life on Mars is led by the Perseverance rover. Unlike earlier missions, Perseverance was designed specifically for astrobiology. It explores Jezero Crater, once a river-fed lake with a well-preserved delta. Deltas are important. They concentrate sediments. They trap organic material. They protect delicate structures from erosion. They are among the best places on Earth to preserve signs of ancient life. Perseverance has identified carbon-bearing minerals and fine-grained sediments formed in water. It has drilled cores from carefully selected rocks. Each sample is sealed, stored, catalogued. These samples are not meant to be analyzed fully on Mars. They are meant to come home. Future missions are planned to return them to Earth, where laboratories can study them with instruments far more sensitive than anything carried by a rover. If Mars ever hosted life, these samples offer the best chance of finding its traces. Not guesses, not indirect clues, but physical evidence that can be tested and retested. The search does not end with the past. The surface of Mars today is harsh. Intense radiation, extreme cold, very low air pressure. Conditions that make life difficult to sustain. Yet underground, the story may be different. evidence suggests that liquid water may still exist kilometers beneath the surface, protected from radiation, insulated from the cold, possibly stable for long periods of time. On Earth, life thrives deep underground, far from sunlight, using chemical energy instead. Entire ecosystems exist without ever seeing the sky. If life ever arose on Mars, it may have retreated below the surface as conditions worsened. Sheltered, persistent, difficult to detect. This possibility keeps Mars at the center of astrobiology, not as a dead world, but as a quiet one. Looking ahead, Mars is also central to humanity's future in space. Plans for human exploration are already taking shape. Humans could drill derail, analyze samples in real time, adapt exploration strategies in ways no rover can. But this comes with responsibility. Any search for life must avoid contamination. Mars must be studied carefully, without bringing Earth's biology with us. Mars matters because it is close, because it is preserved, and because it represents a natural experiment. Two planets formed at the same time, from similar materials. One became alive. The other, perhaps, did not. Understanding why may be one of the most important scientific questions we ever answer. Because Mars is not just about Mars. It is about life itself. How it begins, how fragile it is, and how rare or common it may be in the universe. The search for life on Mars is not over. In many ways, it is only just beginning.